All right, hello everybody. Welcome to our, I suppose, first CU Prime talk up from the 11th floor of this semester. So if you do not know what CU Prime is, we're a student group that's promoted to, or designed to promote allyship, equity, inclusion, diversity in the physics department and beyond. So we got our start more than 10 years ago. And ever since then, we've been running mentorship programs and a class that runs each fall. It's offered especially for first year students, and a talk series. So our goal with these talks is to present research in a way that personalizes the speaker, but also helps you to understand science in a jargon-free way. And so today we're going to hear from Kenny Higginbotham, who is a fifth year graduate student, who's going to tell us about his research about black holes. So these talks are a bit different than the normal seminars you might usually attend. The main difference is that throughout there will be times for you to discuss with your neighbors and get to know one another. That way we can, really learn about science, not just by listening to somebody, but also by talking, which is how a lot of people learn. So don't be shy. Feel free to interrupt at any point if you have any questions. We're happy to answer them. And with that, I'll let you take it away.
Thank you, Tyler.
Join me in welcoming Kenny.
Well, thank you for having me for your CU Prime talk this month. I'm really excited to tell you about some exciting developments in black hole information recently. So I understand that CU Prime speakers often share a little bit about themselves and their journey in physics. So I'll start with that. I grew up in a town called Warner Robins, Georgia. It's basically right smack in the middle of the state in that red dot. The special thing about Warner Robins is it plays host to Robins Air Force Base. So there's a picture here of the F-15 stationed outside of the Museum of Aviation near the base. So it's probably not a surprise that I first fell in love with science because of flight. So I loved planes and birds. I was an avid bird watcher. And I was obsessed with flight as a kid. I picked up my first physics book in middle school, around 7th or 8th grade, and it was on the physics of absolute zero. So how we've gotten as close as we can to absolute zero temperature. And I came up with my first theory in high school. It was called trough theory. It was about how electrons move between orbitals of an atom. It's completely terrible. You should not study it. But I was very thankful to have teachers both in middle school and high school that encouraged me to pursue my passions and dreams. And so I'm very thankful to them. And they're the reason I'm here today. So for undergrad, I attended Georgia Tech in Atlanta, Georgia. And I graduated in 2019 with a bachelor's in physics. And along the way, I did some research as an undergrad. My first research experience was through the RU program. RU stands for Research Experience for Undergraduates. It's a program funded by the NSF that allows students to attend colleges around the country for a summer and do a research project with an advisor. And so at that RU, I attended Louisiana State University, and I studied temperatures below absolute zero, so temperatures negative Kelvin. 2 summers later, I attended a SULI program. So SULI stands for Science Undergraduate Learning Internships. That's a similar summer program funded by the DOE. And so there I was actually at SLAC National Lab near Stanford for the summer. And there I studied simulations of particle collisions. And I first introduced the particle physics there. Throughout my time at Tech, for 3 out of the 4 years, I did undergraduate research around binary black hole mergers. In particular, I studied simulations of mergers. So I got to play with those, and that was a lot of fun. I also have a picture here. I was very involved in the marching band at Georgia Tech. I played trumpet, so great way to de-stress outside of classes. In 2019, August of 2019, I started here at CU as a grad student. As Tyler said, I'm now a 5th year grad student. My advisor is Professor Oliver DeWolf. He and I have studied a number of topics in high energy theory. And most recently, we've been thinking a lot about black hole information, which is what I'm here to tell you about today. Again, I think it's important to get involved in things outside of the classroom, outside of physics, so you can de-stress in between tests and homework. And so here I've been involved in the Graduate Christian Fellowship and also the Grand Canonical Ensemble. If you've taken statistical mechanics, you'll recognize the grand canonical ensemble. But here it's a name of a band. So a bunch of physics students and students from other departments have gotten together under the leadership of Tyler here, and we've put together a band and have a lot of fun. So if you play an instrument and want to join, I encourage you to do so. So enough about me, let's get into some physics. But before I tell you about black holes, I want to tell you about the physics of information. So all of the computers that we use, including this computer and all the phones that you have in your pockets, they describe the world in terms of bits. And one bit can either take on the values of 0 or 1. 0 or 1. So the computers describe the world in these bit streams, like the one I have shown here, and they do math and display graphics and communicate with each other using these bits. Well, quantum physicists describe the world a little bit differently. They use qubits for a quantum bit. This is a quantum bit of information. Qubits are special because they can be 0 and 1. So here I have one qubit. This qubit can be in the 0 state, it can be in the 1 state, or it can be in both, what we call a superposition of 0 and 1. And this allows us to describe the world in much more complex ways. Now, quantum mechanics tells us that information is conserved. I want you to think about this a little bit like the conservation of energy. So we know that energy is always conserved. It can take different forms. So for example, potential energy that you might get from gravity can be converted to kinetic energy or even thermal energy, but it's always energy in some form. Information is similar. Information cannot be created or destroyed. It's always there, and we can manipulate it. And then sometimes it gets spread out amongst the larger system and shows up in different forms, but it's always there. It never goes away. Okay, so now I want you to think about a diary. I actually have my diary right here. Please don't look at it. It's very private. But let's say I have some information written in my diary that I really don't want y'all to see. Like, it's just too embarrassing. So by raise of hands, can someone tell me what's a good way for me to get rid of my diary so no one can read it? Yes.
Burn it, bury it.
Absolutely. So burning it, I want to focus on burning it. That's a great way to get rid of a diary. So I'm going to have our first discussion question here. So knowing that information is conserved, where did the information in my diary go after it's completely burned? And as a hint, I want you to think about what's left over after the diary has finished burning. So turn to your neighbor. If you don't know them, introduce yourself, and then talk about where the information in your diary went. All right, everyone, let's come back together. I heard some great discussion. So can someone please tell me, where do you think the information went after I burned it? Yes.
My first thought was smoke,
Smoke.
but the smoke still has some organization. Is the information still there? Maybe.
Maybe, yeah.
Trent had the idea. It's still in your mind.
It's still in my mind. You know, we haven't burned my mind, and that's a good thing.
My
Great.
reaction was, what if you die?
You know, that's a really interesting question too, and I won't cover death in this
I
talk.
think that's pretty cool.
Yeah. So we have smoke. Any other ideas? Yes.
We kind of talked about like the information was still kind of there, but like in the process of burning it, you convert it into form. So it's like some kind of like energy exchange or increase in entropy that's associated with change.
Okay, good. Any other places besides smoke or some energy transfer? Ashes, great. Yeah, there's going to be, you know, some crumpled up paper in the ashes, and there's going to be some information there. Great. Well, I love these ideas. So we already said ashes, we said smoke. One other thing I want to say is the light radiated by the flames. That carries information too, because the ink in the page is going to determine how the flames burn. And how the flames burn is going to determine what light is emitted from them. So the light's going to carry some information as well. And then last but not least, I think we kind of talked about the energy transfer. So the movement of air molecules, there's going to be some thermal energy that's transferred to the air. And that's going to, you know, depend on how what I wrote in my diary as well. So all of the words in my diary are now super scrambled up in all of these things. And I claim that if we could keep track of every single little bit of this information, all of the particles, every single bit of ashes, all of the light, then we could reconstruct the diary. So you might be able to come up with some computer model that tracks all of these particles, and then we could work the physics backwards to reconstruct the diary and what was written on it. Now, this is really hard. I mean, we can't do this with our current level of technology. Like, if I burn this diary right now, no one in here would be able to do it. But in principle, quantum mechanics tells us it's possible. So even if I burn my diary, if one of you were super dedicated to figure out what was inside, physics tells you you can do it. Okay? Now, I also want to mention that if you miss any one of these ingredients, like if you forget to collect the smoke or if you forget to collect the ashes, then this reconstruction is not going to be possible. You need every single last bit of information to be able to do this. Okay, great. Now, this talk isn't just about burning diaries, so you might be able to think where I might put my diary next, and that might be a black hole. So let's remind ourselves about some facts about black holes. So first, black holes are created by taking a massive object, such as a star, and collapsing it down to a really, really, really small object. So I've compressed it down to really large density. Now, inside of a black hole, the gravity is so strong that not even light can escape it. And there's this point of no return, this boundary where if I go past it, I can't come back out. And that point of no return is called the event horizon. Now, black holes are very extreme objects, but they're actually relatively simple. And I only need 3 things to describe a black hole. If you tell me these 3 things, I know exactly what the black hole looks like. The first is mass. You know, what was the mass of that star that I collapsed down to a black hole? How much mass does it have? The second is charge. A black hole can be positively charged, it can be negatively charged, or it can be neutral. And the third is spin. So if I take my black hole, I can spin it, and it gets some spin as well. Now, what happens if I throw my diary in there? Well, mass, spin, and charge aren't enough to describe all of the words in my diary, right? So if I take my diary, it has some mass, I throw it into the black hole is going to grow by that amount of mass. If I put some charge on there, let's say maybe the ink is made of a bunch of electrons, and I throw my diary into the black hole, that black hole is going to take on that charge the diary had. And let's say I start spinning, and then I throw it into the black hole will acquire that spin as well. Okay? But that information isn't enough to say what's inside my diary. It's not enough to say that, you know, on this page I wrote this word. So just by looking at a black hole, I can't tell what the diary says. So where did the information go? Well, the prevailing belief for a long time is that the information contained in my diary is now locked behind the event horizon. It's there, we just can't access it. So you can think of like a vault. Maybe I put my diary in a vault, I lock it up, and I throw away the key. The diary is still there. The information is still there. I just can't get to it. The only way to get to it is open up that vault and go inside. Similarly, the only way to get the information in a black hole is to jump into the black hole and read the diary. But then you can't communicate with anyone on the outside, and you're doomed to die. So, all right. But that's not the end of the story, or else the talk would be over here. Let's add some quantum mechanics. So in 1974, which is 50 years ago this year, which is pretty incredible, Stephen Hawking incorporated some quantum mechanics into black holes, and he found that black holes aren't entirely black. They actually radiate. And as they radiate, they lose some of their mass. So let's follow the life of a black hole. So we take some massive object like a star, we collapse it down to a really small point, and we get a black hole. This black hole will start to evaporate by emitting Hawking radiation, which here I have as little red squiggles. And it will continue to do that until the black hole is completely gone. And there's nothing left but Hawking radiation. Okay? Now, I want you to, yes, you question?
Nothing left of Hawking radiation that had radiated earlier.
Yes, while the black hole was evaporating. Yes, exactly. Great. So I want you to discuss with your neighbor now, what happens if I throw my diary into this black hole? So I throw it into the black hole, I let it evaporate. Where is my diary now? So turn to your neighbor and discuss. All right, friends, let's come back together. So I threw my diary into this black hole. It evaporated, it's gone. There's only radiation now. Where is the diary? What do you think? Yeah.
Sorry.
In the radiation. That's a great guess. Like, there's only radiation left. That's the only place it can be. Well, I'm here to tell you that our current best theories disagree with you. All right, so let's get into that. So there's a paradox. The radiation only knows about mass, spin, and charge. That's the only thing the black hole knows. That's the only thing the radiation knows. So if I take a piece of Hawking radiation and I ask it, where is the diary? It's going to say, what diary? The radiation knows nothing about the diary. All right. So information should be preserved. So where did the diary go? There's nothing else. This is the essence of the black hole information paradox. We know that information should be conserved, but when we throw information into a black hole and it evaporates, the information appears to be gone. Yes.
Why does information need to be conserved?
Quantum mechanics demands it. It's a property called unitarity. But this is a well-studied property of quantum mechanics. So if information is destroyed, then we'd have to like redo quantum mechanics. Yeah, question.
So like Nether's theorem, is there a associated symmetry?
It's related to conservation of probability. So quantum mechanics deals with probabilities and it's related to conservation of probability. Good question. Great. Okay, so let's get into some possible solutions to this information paradox. The first is called remnants. You know, maybe the black hole doesn't completely evaporate, and there's something in quantum mechanics that prevents the black hole from completely disappearing. And there's something left there at the end. So there's radiation and then something. And maybe that something encodes all of the information that the diary contains. Now, this is kind of an appealing possibility, but none of our theories suggest that this is true. There's nothing coming from our current understanding that says, oh, there might be a remnant there. So let's move on and think about something else. We could take seriously the idea that information is actually destroyed. And this would actually lead to something called a firewall, which you may have heard before. It's this wall of super high energy stuff right behind the horizon that annihilates everything that comes behind the horizon. And this would actually destroy all information. But this violates quantum mechanics, right? We'd have to completely throw out quantum mechanics and start over. Not super appealing. Quantum mechanics does a lot of good for us. So we'd like to keep that around. So let's not worry about firewalls. The third option, let's go back to radiation. Maybe the diary really is in the radiation. But our current theories don't tell us how it gets there. If that's the case, and there's a lot of evidence that points to number 3 being true, then we need a more fundamental theory. Our current theories aren't enough. They're missing something. And so we call them effective, that they're correct in some places, but when you go to something like a black hole, they're not true anymore. And there's something more fundamental that is true. And we need that more fundamental theory to tell us how the diary got to the radiation. So we don't know what that more fundamental theory is. It's presumably some theory of quantum gravity, but we don't know what that is yet. So we're going to stick with our effective theories, and we're going to ask, what can we still learn from them? We know they're not enough, but they still have some nuggets of truth in them. So what can we still learn from them? So that's what we're going to ask today. And we're going to do that by talking about 2 astronauts. So we're going to talk about astronauts Alice and Bob. They're out in space. So Alice is going to be this orange astronaut. Bob is going to be this blue. So Bob, blue, Alice, A for A range, I guess. But you can tell them apart that way. And Alice and Bob come across a black hole. And Alice really wants to know what's inside a black hole. So she's going to bravely jump in and she's going to find out. Bob, he's a bit more cautious. So he's going to wait outside. He's going to say, I'm going to just wait and watch the black hole evaporate. And I'll figure out what's there at the end. So he's giving us a thumbs up because he's cool just sitting outside the black hole. So let's follow the perspectives of both of these astronauts. So Alice is going to see the interior of the black hole given by our current best theories. So these are these effective theories that we know aren't quite good enough, but they tell us some truth. So in particular, Alice is going to see a smooth interior. And what I mean by that is there's no firewall. So she's not going to run into anything behind the event horizon. There's nothing to stop her from falling in. She's going to have this nice, smooth journey into the interior of the black hole. Second, she's going to see Hawking radiation given by something we call pair production. Now, this diagram on the right illustrates what pair production is. So this black curve is supposed to illustrate the event horizon. Remember, this is the point of no return. Once you cross the event horizon, you can't come back out. So to the left of this line, this event horizon is going to be the inside of the black hole. And to the right of the line is going to be the outside of the black hole. Now, in one of our theories called quantum field theory, which is our best understanding of quantum mechanics so far, we have this thing called pair production, where a particle-antiparticle pair can appear out of the vacuum and then annihilate. And this is happening all the time, all over, like in your body, in the chair, in space around us. It's always happening. But suppose that this pair comes into existence on either side of the event horizon. Well, the one on the left side of the event horizon, it has to fall in. It can't come back out. And the one on the right side of the event horizon is an escape away. So they're going to separate forever. They're going to be twins, forever separated. One fell into the black hole, one escaped away. The one that escaped is what Bob sees as Hawking radiation outside the black hole. This is the Hawking radiation that causes the black hole to evaporate. Alice is going to see the one that fell in. Now, I put a little asterisk here next to pair production because this is a toy model of Hawking radiation. Toy models are important in physics because they help us to understand really complex ideas, but they only capture some of the ideas, not all of them. So this is not a perfect picture of Hawking radiation, but it's going to be good enough for what we're going to talk about today. But if you were to like poke and prod this picture some, you would eventually find that it kind of breaks down. But that's okay. It's going to serve our purposes for the moment. So we're going to stick with it. Yes.
Suggesting all the Hawking radiation is due to this pair production?
Yes, that's what I'm suggesting. It's at least the picture I want you to have in your head. Yeah. Yes.
So then, if there's this pair production and like one particle goes inside and one goes outside, like wouldn't that just mean that like while the black hole is like gaining or losing some energy or whatever, so that it eventually goes, it's also gaining something?
Excellent. So you're starting to poke it where the toy model starts to break down a little bit. What I haven't told you is that particle that falls in actually has negative energy. And so it's actually eating away at the energy of the black hole. That's really difficult to see from this toy model. You really need the full tools to be able to see that. But I will give it to you as true from the moment. Great question. Okay. So because of this pair production, the third thing that Alice sees is an ever-growing number of particles inside the black hole. So this pair that fell in, she's always going to see an ever-increasing number of these. And we can understand particles as information. So Alice is going to see an ever-growing amount of information inside the black hole. Okay, we'll come back to that point. But in the meantime, let's go over to Bob. So remember, Bob is sitting outside the black hole. He's watching it, and he's describing it in terms of these more fundamental theories that we don't have yet, but suppose Bob does. And he understands the evolution of the black hole in terms of these more fundamental theories. We already understand that in these more fundamental theories, the amount of information inside a black hole is actually given by the size of the area of the event horizon. So I have two black holes here. The black hole on the left is larger, it has a larger surface area, and the black hole on the right has a smaller surface area. So that means the black hole on the left is going to have more information inside of it than the black hole on the right. So as Bob is watching the black hole evaporate, it's getting smaller and smaller and smaller. So that surface area is decreasing, which means the black hole that Bob observes contains less and less and less information. All right, so let's compare these two perspectives, the perspective of Alice and Bob. So remember that Alice is seeing an ever-growing amount of information because of this pair production picture that we talked about. But Bob is seeing an ever-decreasing amount of information because the surface area of the black hole is shrinking. Now, at some point, the black hole in Alice's description will have more information than the black hole in Bob's description. Now, this really doesn't make sense because Bob's theories are supposed to be more fundamental. They're supposed to describe everything that's going on in Alice's theory. So if Alice's theory has more information than Bob's, then how can Bob's theory describe everything that's going on in Alice's? It doesn't really make sense. And this was a problem for a long time. We didn't understand how to deal with this. Why the more fundamental theory should have less information in it. Like why? That doesn't make any sense. Until about a year and a half ago. So a year and a half ago, a paper by 5 authors came out in August of 2022. My advisor actually came up with the acronym FIVA because we thought it was fun. We've caught the FIVA. So FIVA stands for the name of the 5 authors. That's Jeff Pennington, Daniel Harlow, Netta Engelhardt, Shreya Varden, and Chris Akers. Fun fact, Chris Akers is coming here to see you as a professor this fall. So if you're more interested in this black hole stuff and this black hole information, he'll be another great person to talk to. So you can go bug him. What FIVA did is they developed a map from Alice's description to Bob's description. Now, what do I mean by that? So suppose Alice carries a quantum computer with her inside the black hole. So I've got the black hole here, Alice is inside. She's got her computer, it has the obligatory atom on it to show that it's a quantum computer. And this quantum computer is programmed with this map that FIVA developed. Now, what Alice can do is convert all the information she sees inside the black hole into qubits, that quantum bit of information that we talked about. And then she can feed it into her quantum computer. This computer will perform the map, and it spits out on her screen an image of what Bob is seeing. So it takes Alice's information, and it tells you what Bob is seeing from the outside. So Alice can know what's the perspective of Bob outside. Now, this map is really weird because remember, Alice has more information in the black hole than Bob does. So what this map has to do is throw away some information. It has to chuck it into the trash can. Now that's weird. Like, we don't do that. That's like a huge taboo in quantum mechanics. Remember, I said information was conserved. So we only talk about maps that conserve information. But what FIVA is proposing is a map that destroys some information. So it's a little bit bizarre, but we'll see that it's okay. So, we've been talking about this diary. What does this map have to say about the diary? Well, suppose Alice carried her diary into the black hole with her. She sees the diary in her hand. The Hawking radiation doesn't know anything about it. Remember, Hawking radiation is given by this pair production. So the outgoing particle, that's the Hawking radiation, has nothing to do with the diary. It's never seen it. It doesn't, it hasn't opened the pages and flipped through it. The Hawking radiation going out doesn't know anything about the diary, which matches with our current understanding, our current best theories. But what about Bob? Where does Bob see the diary? What Alice can do is take her diary and the information around her and feed it into this map. And the map will tell her where the diary is from Bob's perspective. So in Bob's description, where is the diary? Alice can find out with this map. So let's see, FIVA says, miraculously, the map shows that Bob sees the information in the radiation. So now, with this map, if Bob goes and collects the radiation and asks it where the diary, and it says, oh, that diary, now the radiation knows about the diary. So even though this map is really bizarre, it throws away some of Alice's information, it gives more evidence that the diary can be reconstructed in the radiation. Now, the map doesn't tell us how the diary gets the information, it just tells us that it does. So it's still an open question as to how the diary gets the radiation, but we know it should be there. And that's a big step forward. Now, just as with burning the diary is going to be really hard to reconstruct with the radiation, right? It's going to be virtually impossible. It's theoretically possible, but actually doing it is going to take a long time. But in principle, Bob could do it. One more thing I'll say about this map is it's really incredible that all of this came from just a toy qubit model of the black hole. Remember, I talked about Alice converting everything she sees into qubits and then feeding it into her quantum computer. So all we've done is created some simple qubit toy model of the black hole, and it shows us that the diary should be in the radiation. And that's really cool because there's still so much about black holes that we can add to this map, and we haven't even got there yet, and we're still getting the right answer. So that's really cool. Okay, let me tell you about some ongoing work that my advisor and I have been doing for the past year. So Phoebe's map makes an important assumption. And they say that once Alice jumps in, nothing happens to her, right? She jumps in and she's just chilling. She's checking her watch. She's writing more in her diary. Nothing's going on. Now, that's not quite physical. Things should happen to her. If you've heard of spaghettification and all that fun stuff, you know, that's something that would happen to her inside the black hole. And it's okay to make assumptions. Sometimes when we come across a hard problem, we have to make an assumption to make progress. And once we've made that progress, we can come back and reevaluate that assumption. So that's exactly what my advisor, Professor DeWolf, and I have been doing, is reevaluating that assumption. And we want to add non-trivial dynamics for Alice through a new map that we call the backwards-forwards map. And I'll describe that to you now. So the first step of the backwards-forwards map is to time evolve backwards in Alice's description. So we're going to take Alice, and we're going to undo all of those interactions with particles and whatnot that she has inside the black hole. We're going to undo her spaghettification, and she's going to pop out of the black hole in this backwards time evolution. And then everything else that would collapse to form the black hole is going to pop out as well. So I've illustrated here, you know, Alice is coming back out of the black hole, and I put a red circle around her to emphasize this is from Alice's perspective. Now, once everything, Alice and the star, are back outside the black hole, once we've undone all of the time evolution from Alice's perspective, Bob and Alice are now both outside the black hole, and they both agree in their descriptions. They're both seeing the same things. They both see the same star. Everything agrees. Nothing in their descriptions are different. That means we can now switch to Bob's description because it's the same. So we're going to switch to Bob's description and evolve forwards in his description. So he's going to watch Alice fall into the black hole, and he's going to describe everything that happens in terms of his more fundamental perspective. So this map together starts with Alice, backwards evolves, and then forwards evolves in Bob's description, is a way to convert the black hole information from Alice's point of view through this backwards forwards map to Bob's description of the black hole information. So this is another map from Alice to Bob. And so, for example, a quantum computer could be programmed with these steps, and Alice could jump into the black hole with her computer, and then she could model this backwards and forwards time evolution on her quantum computer and see what Bob sees and understand what he's seeing. Okay, to give you a little taste of what that actually looks like when we're doing our calculations, I put this on the right. So this is a quantum circuit diagram. So if you take quantum information and computing, you'll learn about these diagrams, but let me give you a taste of what it means. So each of these lines, the orange and the green and the blue and the red and the black lines, describe qubits. So these are the qubits of information inside the black hole, and we're going to do some operations to them. So these boxes are operations that we do to the qubits. The input goes into the bottom, the output comes out the top, so that's indicated by the arrow. So in particular, Alice is going to convert everything she sees into qubits of information, and then she's going to input that to the orange, green, and blue lines at the bottom of the circuit, and it's going to run upwards. So this brown box is undoing all of the time evolution from Alice's perspective. It's running that time evolution backwards. The black box at the top is performing Bob's time evolution. So that's the time evolution in the fundamental perspective. And then out the top comes the black and the blue lines. That's the black hole information and the radiation information from Bob's perspective. So Alice puts in at the bottom, performs these operations given by the boxes, and outputs Bob's information at the top. Now, I told you that this map has to get rid of information. And if you look, there's the green and blue lines coming together at a point right below max. This is where we throw away information. And what this is actually modeling is if you run Alice's time evolution backwards, those Hawking pairs that were produced by Hawking or by pair production come back together. And when they meet, they're going to annihilate back to the vacuum. They're going to disappear. That's exactly what those lines represent. So the way we throw away information is by the backwards evolution of Hawking pairs. Now, once we have this circuit diagram, we can do lots of things with it. So we can actually do math and calculations with this circuit diagram and compare it to Phoebe's result, which is really cool. I made that circuit diagram sometime last year, and I had a lot of fun doing it. So yeah, I think it's pretty cool. Okay, enough about physics, enough of me tormenting your minds. So let me tell you about what's a day in the life of a theoretical physicist. So my day involves a lot of reading, right? Because as all physicists, we have to understand what came before us, what we already know, the literature behind the subjects that we're studying, so that we can base our new theories in a well-grounded way, and learn what we can add to them. Every morning I check the archive. It's spelled with an X. But what the archive is a free preprint service. So physicists around the world, as they're publishing papers, will submit their paper to the archive before they go and publish it at a journal. And it's free. Anyone can go and look at it and access it. And so you can see what new papers are being posted. So if you want to check it out, I highly encourage you to do so. Just go to archive.org and you can look at all kinds of different subjects. You can look at high energy theory. You can look at gravitational physics. You can look at condensed matter experiments. Whatever interests you, you can see all the new papers in that field for free, completely for free. Second, I do a lot of pen and paper math. So I actually drew this diagram on the right a couple of weeks ago. And what I'm doing here is taking that circuit diagram I showed you on the last slide and beefing it up a little bit. So I get to have a lot of fun drawing really cool pictures and doing math with them. And that's something that excites me. And I enjoy that a lot. This picture in the middle I made with Python just this past week. So I do a little bit of Python programming here and there, a little bit of coding with Mathematica. So those are two tools that I use. They're helpful to me. I don't do them a ton. Again, I do more pen and paper math than I do computational, but it's a useful tool sometimes because I would have a hard time drawing that by hand. And lastly, I do a lot of writing. Because it's all well and good if I come up with a new great idea, but it does nothing if I don't share it with anyone. So exactly like I'm sharing new ideas with you right now, I have to share my new ideas with the greater community. And I do that by writing papers and posting them on the archive. So I use a program called LaTeX. It's actually like a coding language that you use to write papers, but you can write really nice equations and really nice tables and really nice figures. Actually, the circuit diagram on the last page, I actually used LaTeX to draw that, which is kind of crazy. To use LaTeX, I actually use Overleaf. It's a free website. You can go make an account at overleaf.com, and then you can use LaTeX to your heart's content. And you can actually collaborate with people as well. So my advisor and I will both use Overleaf and collaborate on writing a paper together. So those are some tools that I use every day, and maybe you want to check out. But other than that, hopefully this AI picture makes a little bit more sense to you now. If it doesn't, that's okay, because it's AI. But thank you for your attention, and I look forward to your questions. Yes.
Does Alice actually reach past the event horizon such that she would see the extra information that you're talking about?
Yes, as long as there's no firewall to obstruct her, she will pass through the event horizon.
How do we get there? I've heard that it's impossible to actually pass the.
What you might be thinking of is from Bob's perspective, due to gravitational time dilation, Bob will never see Alice past the horizon. He'll only see her like slowly approach it after a very long time. But from Alice's perspective, she does pass through the horizon. Yes.
As I hypothetical, if you had like an angled particle and threw it into a black hole, like would we like if information like nothing can get out of black holes, but then like the information get out still?
Good question. So you were saying I have two particles that were entangled,
Yeah.
and then I throw one in.
Yeah.
What happens to that entanglement? Later, that particle that's outside will be entangled with some amount of radiation. So that entanglement is going to be spread amongst the radiation outside the black hole. That's what should happen. That's what we believe should happen. Again, our current theories don't say that, They say that entanglement is gone, if you will. But it should be in the radiation. Good question. Yeah.
So, does this like radiation, does it like pop into existence for the particle and two-particle, whatever? Is like come into existence like right outside the event horizon or something like that, so that one can escape or something?
Yeah, so there's many different ways to think about it, and many different ways to actually do calculations. Probably the easiest picture to have in your head is that they pop in on either side, and so one goes away and one falls in. You can also think about them appearing on the outside, and one like tunnels through the horizon. If you've heard of quantum tunneling, it tunnels through the horizon, or maybe they both appear on the inside and one quantum tunnels out. But the easiest picture is to just pop on either side. And again, this is just a toy model, so take it with a grain of salt. Okay.
So anything that goes into a black hole eventually turns into radiation?
Eventually turns into radiation. Yeah. That's what we believe should be true. We don't know how yet, but the evidence of this map and lots of other evidence shows that that should be true. Yes.
If the black hole, it sounds like it's constantly getting more and more particles. So how does that make it go away?
Yeah, so that goes back to a question earlier, how the particle, the part of the pair that falls inside actually has negative energy. And so it's chipping away at the energy of the black hole, and so it's losing mass. And so that's how it goes away. Somehow that, there's something to do with the singularity, that these particles will eventually reach the singularity. We don't quite know what happens there because our theories blow up. They're no good at the singularity. So that's still an open question as well.
So can I ask, you had mentioned these set of works from a couple of years ago. And I remember hearing around that time news articles saying like the black hole information paradox has been solved. So it has it, from your own perspective as someone who works in this field, has it been resolved? And if not, like what would it take to get to that point?
That's a great question. So yeah, you're probably referring to some articles that came out in 2019, when some other papers unrelated to this one showed like really the first big piece of evidence that the diary should appear in the radiation. So that's really when I was saying, we have evidence for number 3 back in 2019. That's when that evidence was really found. So I would say that the paradox has not been solved yet. What I would say is that these things that I've been talking about point to the existence of a solution. We know that there should be a solution to the paradox. We just don't know what it is yet. And it would really take a quantum theory of gravity to understand what that solution is. So, there's lots of progress being made in string theory or loop quantum gravity that maybe one day can teach us more. So we know there is a solution, we just haven't found it yet. Yes.
So like, are you only working on like quantum information, or because it's like connected to other things? Are you also, like you said, you need the theory of quantum gravity? So then are you also working on that as well?
So we've found that quantum information and tools from quantum information are really helpful in trying to understand properties of quantum properties of gravity. So if you've heard of the holographic principle, ADS-CFT, those are tools that I use a lot, and they have really strong connections with quantum information. So it doesn't tell us everything, it doesn't give us quantum gravity, but it can tell us a lot about the nature of quantum gravity. And so we use quantum information tools and things like this to be able to try and pick apart some of those pieces of information. Yeah.
How high is the gravity in a black hole? Is it based off the size of the star that, or like, what's that?
Yeah. So when we measure how high the gravity is, we often talk about the curvature of space-time inside the black hole. And that is directly related to the mass of the black hole and the mass of the star that collapsed to form it. Yeah.
Questions for any? Well, if not, if you're, oh, yes.
I was wondering, you said that the strongest evidence for the Hawking radiation encoding the information that is encoding the information that is being lost. But if the Hawking radiation is consisting of particles that were created outside the event horizon that escape, those particles technically never see the inside of the black hole.
Right.
So in what sense do they?
Good. So, question was, we've been speaking about, this evidence that the radiation should, encode what fell into the black hole. But the radiation never saw the inside, so how is that possible? Again, our current theories of gravity and quantum mechanics don't tell us how it's possible. We have to do some we have to put some extra tools on top of our current theories in order to get that result. So, for example, this map that I've been talking about is one of those tools. It kind of serves as a proxy for the actual dynamics going on inside the black hole. So we don't know what that actual dynamics is. We have to use something else to serve as a proxy to get the correct result. So this map and other tools that came out in 2019 serve as those proxies for what should be going on. So that doesn't tell us how the information comes out. It just tells us that it does. Great.
Great. Well, if you're here in person, be sure to sign in with that QR code if you haven't already. But otherwise, not that one.
Not that one, sorry.
But yeah. Otherwise, let's thank anyone for.